carry on. So now it is almost 11 over. So you can carry on, no issue. Okay.
Good morning to all. My name is Gaurav Kumar. I'm the PhD scholar in the Department of Electrical Engineering at NIT Rourkela. Today I'm going to present interfacing of C2000 Launchpad with MATLAB, and also I will show you how to generate the PWM signal through the C2000 microcontroller. These are the contents of my presentation. First, we go through the installation procedure. Then we see the Launchpad features. What what are the features and what are the pin details of these C2000 Launchpad. Then we go for the GPIO module. GPIO stands for General Purpose Input Output Module. Then we see how to generate the PWM pulses through the GPIO module. Then we go for the EPWM module. It is enhanced pulse width modulated module. It is called enhanced because we can change the duty cycle frequency and pulse width whatever we want in a fine manner. Then we go for the how to generate the PWM pulses for up or down counter. Then how to give the dead band, how to generate the complementary pulses. Then we go for the up down counter mode. Then we go for how to generate the phase shifted pulses. Then at last we go for signal conditioning circuit, why it is needed in the in the sensing circuit. Then we go for the DAC and ADC module. Then we go for the some closed loop controller of MPPT, which is done through PSO or PNO. Moving to the next slide, this is the installation procedure. First, we have to go to the MATLAB. I will show you. Then we have to go to the add-on. Okay. Then we have to search for the embedded coder support package for Texas Instrument. Okay, this one is the embedded coder support package for C2000. Then we have to go to the manage section. Then we go for the setup. Firstly, we have to install it. Actually, I have already installed, so install icon is not coming. So we install it, then we go to the setup. Here we have to select the our launchpad, what we are using. Okay, so we have the launchpad of TI Delfino F2837XT. So we have to select it. Then we have to go for the next. Then we have to install these third-party software, because at last we have to generate it the code which can be made through the Simulink block diagram, or we can also write the code in the Code Composer Studio, and that code is actually dumped through the cable to the C2000 microcontroller. So these are the external third-party software which we need to install. So we have to go for the next. After installation, then we have to validate it, then it will be completely installed. Okay, this is the installation procedure. So I'm canceling it because it is already installed. Moving to the next slide. Okay, TMS320 F283790 Launchpad is basically a 32-bit floating point microcontroller unit. It is used for the sensing and processing of the data. and also it has two core CPUs, and both the CPUs are of 32-bit, and it has a clock frequency of 200 megahertz. That is, it can take 5 nanosecond to execute a particular instruction. It has some trigonometric mathematic unit, and also it has some complex mathematic unit. Uh, that is, if we have some mathematical trigonometrical mathematical function or complex mathematic function in our control algorithm, then it can easily solve it, and it can also it can easily solve and reduces the computing time of the processor. Basically, these are the units actually helps to improve the performance of the C2000 Launchpad. Then we have the two programmable control law accelerator. This is the two program control law accelerator is basically a co-processor. Actually, it is along with the our two CPUs also. Okay, these are the two control law accelerator which are also of 32-bit, and it enhances the performance of the C2000 microcontroller when it is designed, because it is designed so that it can and independently execute the instruction, and it can also solve the complex mathematics unit, and it can give some time to the main CPU so that it can work some other task. Okay, this is the on-chip memory, and we have some 512 KB of flash memory, and 172 KB or 204 KB of RAM memory. Flash memory is, it is the non-volatile, it is permanent in nature, and it is the RAM which is volatile in nature. It is not permanent. When the power goes up, it will delete the data. Moving to the next slide, we have the dual 6-channel direct memory access controller. Okay, it is also of 32-bit direct memory access controller. Direct memory access is something if we have some input output devices and we have to communicate through the memory addresses, then the direct memory access is through the direct memory access controller. The input output device can communicate with the memory locations, memory addresses without the participation of any CPU. So it is a very fast, and the controller which is used for the direct memory access is known as direct memory access controller hardware. Okay, so we have total in our Launchpad C2000 TMS 320F to 3790 Launchpad, and we have total of 169 GPIO pins. Okay, general purpose input output pin. It can work as a input also, and it can work as a output also. For communication peripheral, we have some USB cable, and it is used for the dumping the code which is generated by the code composer studio to the C2000 microcontroller. Okay, this is the galvanically isolated, means your host computer and C2000 microcontroller is separated from an isolated cable, so that so that no noise can affect the C2000 circuit, or no noise can affect the host computer also. There are two controller area network module, ECAN module. Okay, controller area network is something which is if we go for some automotive system, robotics, then then on that devices we have some CAN module. Okay, controller area network module. Like it is like some microcontroller unit also. So with the help of ECAN module, which is present in the C2000 microcontroller, we can communicate with the other automotive system, robotics, and other systems, microcontroller also. So we have two controller area network modules in C2000. And the third is three high-speed serial peripheral interface ports of 50 megahertz. Okay, so we have three high-speed serial peripheral interface. Means if we have to communicate with C2000 microcontroller to the some high-speed devices like sensor, ADC-DAC module, or some microcontroller, then these module is very helpful. Its speed is, you can see, 50 megahertz, which is very high. Then we have four serial communication interfaces. Serial communication interfaces is actually used for also, it is also used for communicating with some sensors, some some real time applications like motor control unit, engine control unit, in which sensor actuators all are there. Okay, And this is pin bootable. Pin bootable means during the booting configuration, it can also initiate the communication. And also when the power is turned on, then immediately after turning on the power, it can initiate the communication. Okay. The UART stands for Universal Asynchronous Receiver Transmitter. Okay. The other is 2I2C Inter-Integrated Controller. This is the module 2I2C module, which is used for the low speed devices communication. Okay. Like display or some sensors which are slow in manner like pressure, humidity. So in that cases, we can use these 2I2C module to communicate with low speed devices. Okay. Now we go for the analog subsystem. We have total F2837 in F2837XT. We have four ADC module. Okay, the four ADC module each, and from ADC module we can sense the analog input. Okay, so the input can be of two types: the single-ended input and the differential input. For single-ended input, there are 24 external channels. Okay, so we have 24 external ADC pins from which single ended input can be sensed. Similarly, we have 12 external channels for differential input sensing. Okay, these are the pins which I am telling you. I will show you in the hardware also. So the single ended input per channel is of 12 bit. That is, if we give the single ended input, it will convert to the 12 bit, means 2 to the power 12 minus 1 data, means it will convert the sensed input into digital value of 4095 within 4095. Similarly, when it sends through the differential input, then it converts into the 16-bit data, means 2 to the power 16 minus 1. Okay, like I think 65536 is there in digital value. Moving to the next slide, we can see in at each ADC module we have sample and hold circuit. Sample and hold circuit is very much essential because it samples the uh, sensed data, and also it holds for some time to convert properly into digital value. Okay, so and the last is we have some DAC output, digital to analog converter output. We have three 12-bit buffer DAC output. That is, we have three channels from which we can take the digital, mm, uh, we can take the output. Okay, and it is 12-bit. Enhanced control peripheral, we have 24 PWM modules, 24 PWM modules channels, in which 16 modules is of high resolution. That is, it means we can finely tune the duty cycle, finely tune the frequency, and all these things. And these are the high resolution channels. A and B both are present on 8 PWM modules. So total, each PW, basically we have total 12 PWM modules in this series, and each PWM module have two channels, one A and one B. Okay, so we have 8 PWM modules in which A and B two channels are there. So these are the 16 high resolution PWM channels. We have deadband support on each PWM channels, and we have some e-capture modules, enhanced capture modules. It is basically used for the uh, it is basically used for the measuring the it is basically measuring the timing. So if we have some pulses, PWM pulses, so it can measure the rising age time, falling age time, and then it can make the difference, and it can find the frequency, it can find the duty cycle, pulse width. So these modules, ECAP modules, is used for finding the frequency, pulse width, and duty cycle. Then the last is three EQEP modules, enhanced quadrature encoder pulse module. It is basically, if we consider some motor control unit or some devices which have some rotating features like direction and speed, so they have a pre-installed quadrature encoder module. Okay, so with the help of EQEP model, we can communicate with our C2000 microcontroller EQEP module to their EQEP module devices. It basically sends the position, direction, and speed of the motor control unit. Moving to the next slide. This is the TMS 320F28370 Launchpad. Here we can see. Okay, this is the USB port from which we can dump the code, and these are the pins. These are the up to for there are total 80 pins are there. Okay, here we can see, and here we can see the ECAN module GPIO pins also, and ECAN modules ADC differential pair inputs also. Moving to the next slide. These are the pin details of the TMS 320F28790 Launchpad. Here you first see these things. So these pins details is given this side. This and these things is details of these pin. Okay. When we go for these pin details, then its details are given in here and here. Okay. Similarly, all pins details are given here, and here you can see there are in F283790 there are total 6 PWM channels, PWM modules, and each module has 1A, 1B, two channels. Some GPIO pins are also there. Some ADC input pins are also there from we can sense the analog input. Some 5-volt pins are also there. There are total 4 grounds on the pin. We can see the grounds are also there. Some DAC output also there. We have 4 DAC output: DAC1, DAC2, DAC3, DAC4. Okay, moving on to the next slide. These are the pin details. You can see from 1 to 30 pin details are here. Actually, every pin can work. It has some different features also. Means it can work as a see the pin number 3. It is work as a GPIO 19 pin, and the same time it is working as a SCI pin also. So the every pin has maybe more than one one features. Okay. So from 1 to 30, these are the details. From 11 to 40, these are the details. And from 41 to 70 and from 51 to 80, these are the details. Okay. Now we go for the GPIO, general purpose input output. As I have told you, it is the general purpose input output pins is actually a 32-bit register, and it can work as an input or output both. And there are total 169 pins. In port A, there are 32 pins. In port B, 32 pins. Port C, port D, port E, and the port F has only 9 pins. And when we set the 0 in the GPIO control register, then it will work as an input. When we set 1 in GPIO register, it will work as an output. And these are the these are the means notation which can we can use in the GPIO pin to set clear and toggle. Set means if it works as an output, clear means it works as an input, and we can also toggle the registers also. Okay, moving to the next slide. Now I will show the how to generate the PWM pulses with the help of GPIO pin. So this is the I have generated 20 kilohertz pulse with 50% duty pulse, 50% duty cycle. Okay, so this is the Simulink model. Okay. So firstly, you have to choose the GPIO pin, which is GPIO digital output. You can search here GPIO. Okay, digital output. And you have to select for F2837XT. Okay, this one. Then we have to go inside it, and we have to select the GPIO pin. We have selected GPIO 0 pin. GPIO 0 pin, you can verify, you can go through the pin details which I have shared. It is a 40 number pin. Okay. Then we have okay it. Then I have taken a pulse generator block. I have to generate some 20 kilohertz pulse. So I have written 20 kilohertz pulse 1 by 20,000. Okay. And pulse width is 50%. Okay. Then firstly, I will show you the pins which I have told to you. Okay, this is the hardware board, target hardware source. You can see. Okay, this is the clocking. Means we have the CPU frequency of 200 megahertz. Okay, we have four ADC module A, B, C, D. You can see. Okay, and we have DAC channels. We have three DAC channels. We have EPWM channels. We have total of 12 EPWM channel modules. 12 EPWM modules, and each module have two channels A, B. So total 24 EPWM channels are there, and you can see the PWM channels is also working as a GPIO pins. So every pin can work as some different features also. This is the ECAP modules. We have the total of five ECAP modules, EQEP modules. We have total of three EQEP modules, I2C modules. We can see I2C modules. We have A and B, two I2C modules are there. Some SCI modules A, B, C, D, four SCI modules are there. SPI modules A, B, C are there. ECAN modules A, B, two ECAN modules are there. Similarly, we can see the GPIO pins here 0 to 7. Okay, when we select 0 to 7, then 0 to 7 pins are there. Then we go for the next, and at last, when we see for GPIO 168 to 175, then there is only one pin, 168. So total of 169 pins are there. External input we can also see. Okay, now we have to select the solver. We have selected the fixed type solver, and this is the solver name, and this is the fixed step size which I have shown. Okay, now I will deploy to hardware. Okay, I have connected through the C2000 deploy to hardware. You can see the view diagnostic. The corresponding code composer studio code is generating here, and it will also dump in the C2000 microcontroller also. Now the code is downloading in the to the hardware. Here you can see the C2000 microcontroller. It is still downloading. Here we can see the 40 number pins. I have connected the DSO. The channel 1 output is connected to the 40 number pin and ground. Now you can see the this process is done. Now you can see the output on this is the 20, 20 kilohertz 50% duty cycle. This is the 20 kilohertz. You can see 20 kilohertz 50% duty cycle is there. Okay. Now we go for the next one. This is the from the GPI open. We can also we have in the previous slide we have used the pulse generator block. Here we can use some repeating sequence and constant block also to generate the PWM pulses. This is the repeating sequence. I want to generate the 2 kilohertz PWM pulses with 50% duty cycle. So I have given the time value is 1 by 2000. Okay. 2 kilohertz. Okay. I have
Yours,
given.
can you share the screen, Gaurav? It is not
Okay. Okay.
shared.
It hangs. So this one. Same problem. Second one. Please wait for some time. Actually, because I'm not able to share the screen. Only told Is the content visible? Am I audible?
Yes, yes, visible.
Visible, visible.
So now we have generated the PWM pulses with the help of repeating sequence and comparator. Okay. And at last, I will show you by running all the modules, because when I am switching on the camera, then it will automatically log out from the my team. Okay, and I'm facing some problems. So I will at last I will run, and I will show the results also. Okay. So here we have used some PWM routing sequence and comparator. I have generated 2 kilohertz and 50% duty cycle pulse. Now we go to the next slide. EPWM module. The EPWM module, pulse width modulated module. We have this is the EPWM block diagram, in which we have some system clock. Okay, system clock is I have told you the C2 microcontroller has 200 megahertz system clock, and it is given to the clock prescaler. Clock prescaler, basically it actually divides the system clock with some fractions, and it will generate some TB clock. Okay, TB clock is basically the prescaled version of system clock. So it is system clock is 200 megahertz, as I have told you. And if we use the clock prescaler is 1 by 2, means it will divide by 2, and TB clock will be generated as 100 megahertz. So in our case, the TB clock is 100 megahertz. Then we go for then the next module is 16-bit time-based counter module. Actually, its main work is to count. Okay, so we have three different counters: up counter, down counter, and up and down counter. So it is basically a 16-bit time-based counter, and there is some compare registers are there. Compare registers in which some values are given. Zero point 0.5, zero point 0.6 means it is responsible for or generating the duty cycle of a particular pulse. This is the compare logic, in which each the the value is compared to a particular threshold value. Then then it is given to the action qualifier. Action qualifier is something in which we have to set that when my signal will goes for set when will my signal will goes for the clear, when we have to do nothing. Okay, when the counter actually moves from when it counter is 0, then it will go for period, but then it will go for compare A, compare B. Then we have to decide with the help of action qualifier that whether we have to set or clear it. Okay, then I have told you that in each PWM mode channels we have some deadband and facility, so we can leave the deadband with the help of this one. And there is some trip zone also, that if we have some fault in the uh, circuit or a converter circuit or inverter circuit, then PWM output is suddenly stopped with the help of trip zone. Okay. Moving to the next slide, calculating PWM period and frequency. How we calculate the PWM period and frequency, which we want to generate with the help of EPWM block. So see this slide. This slide actually, when we want to generate the EPWM pulses with the help of up count, down count, or up and down counter, then we have to follow these is waves. Actually, in case of up counter, we have the we have the increasing sawtooth wave. In case of down counter, we have the decreasing sawtooth wave. In case of up and down counter, we have the triangular shape of EPW, triangular shape of uh, carrier wave. Okay, counter wave. So here we can see, uh, here there are so many terms are there. Some TBPRD is there. TBPRD, this 4 is the value of TBPRD. Okay. 4 is TBPRD, some TB clock is there, TB counter is there. So what is that? Okay, so we have some sawtooth wave which is in up mode. We have some triangular wave which is in up and down mode. So TBPRD is a particular value. Okay, so the maximum value which is when the maximum value up to which the PWM pulses go when the peak is arrived is known as TPRD value. So we can see the peak is at fourth level. So our TPRD value is 4. So TPRD value is just a number 4. Okay. In similarly, if we go for the down counter, in case of up counter, the clock is moving like that. 0, 1, 2 means it is increasing in steps. 0, 1, 2, 3, 4. And again after going to the peak, then again it reset to 0. Then again it will go in increasing manner 0, 1, 2, 3, 4. Then again it will reset to 0. Similarly, in case of down counter, na, it will starts from 4. So TBPRD starts from 4, then it will go down 4 to 3, 2, 1, 0. Okay. So this is the TBPRD value. Similarly, in case of up and down counter, you can see the maximum peak is at fourth level. Okay. The 0, 1, 2, 3, 4. The maximum peak is at fourth level. So here the TBPRD value is 4. Okay. So now we see what is TB clock. TB clock, I have told you that it is basically a pre-scaled version of system clock. And I have told you the system clock is at 200 megahertz and TB clock is system clock. Here you can see EPWM clock is system clock by 2. And here we have taken the high speed clock and clock division as 1 and 1. So TB clock is 100 meg. So this is the TB clock 100 megahertz. But it is in frequency, but here it is actually 1 by TB clock because I am showing it in seconds. Okay. This is the first step timing is known as TB clock. First step timing is known as TB clock. So you can see this timing is known as TB clock. It is in second. So it should be 1 by TB clock. TB clock is 100 megahertz. So 1 by TB clock, if you find it will come 0.01 microsecond. So this is the 0.01 microsecond time period. Okay. And you can see this complete cycle is TB clock, which is which is 0.01 microsecond. The 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 system clock uh, pre-scaled version is TP clock, and the one complete cycle is of 0.01. You can see. And this is the TB counter. I have told you that in case of up counter, the TB counter starts from 0, then it will go for 1, for 2, for 3, 4. Then a TB counter register again set to 0. Then it will again increase, then again decrease. Similarly, in case of TB counter up and down mode, it will start from 0, then 1, for 2, 3, 4. Then again it will down 3, 2, 1. Then it will again go like that. Okay. So suppose if we want to calculate the TPWM, means we have to find the PWM pulses, time period or frequency. How will we find? So here you can see there are 4 TPPRD. 1, 2, 3, 4. Means there are 5 TPPRD because if we consider this one also. So there we have 5 TPPRD value. 4 plus 1. Means TVPRD value is 4 because it is maximum peak, but we have to add one extra because of this gene. Okay. So if we want to find this gap, what is the amount of this gap? So we can tell that it is the gap of TBPRD plus 1, means 4 plus 1, 5. Okay. And if we multiply 4 plus 1 TBPRD means 5 value to the 1 by TB clock, which is 0.01 microsecond, then we can easily find the PWM, means PWM pulse with time period, and then we can find its time frequency. Okay, in case of similarly for down counter also. And if we go for the up and down counter, then you can see this is the 4, 1, 2, 3, 4. TBPRD is 4, but what is the gap from this one to this? Then you can see 1, 2, 3, 4, 5, 6, 7, 8. Total 8 gaps are there. So we have to multiply TBPRD with 2 values. So 2 into TBPRD is this total duration. And we know the each duration is of 0.01 microsecond. So if we multiply 2 into TBPRD into 1 by TB clock, then we get the TWM value in case of up and down. Okay, so these are the steps so that we can find the PWM time period and frequency. And here we have the EPWM clock. EPWM clock is basically the system clock. Okay, and pre-scaled version of system clock. So EPWM clock is system clock by 2. So 200 by 2. We have system clock is 200 megahertz. System clock by 2 means 100 megahertz. And HSP clock and clock division, by default it is 1 and 1. So TB clock is also 100 megahertz. So here we can see the EPWM clock and TB clock is same, 100 meg. Okay, both have the same value. EPWM clock and TB clock have the same value. Okay, now we see how to find up or I have told you formula TPWM is equal to TBPRT plus 1 into 1 by TB clock. So according to that, I have find a TBPRT value. So TBPRT value is TB clock by FPWM minus 1. You can also find TPWM is equal to TBPRT plus 1 into TB clock. From there, you can find the TBPRT value. This is this. Okay, where FPWM is this one. For up and down counter, TBPRD values TB clock by 2 into FPWM, which I have told you from this diagram how this formula came. Okay, and the actually, if you want to see, I'll say if we go for the EPWM pulse, see this. For generating a particular pulse from EPWM blocks, we have to give inputs. Okay, this is the time TBPRD value, TBPRD. This is the compare value input. Here in this block, I have generating two pulses of different and duty cycles. So I have given two different duty cycles and a particular duty TBPRD value. Okay, so here you can see the TBPRD EPWM link. Uh, Here you can see the time period unit, TBPRD value. It, it has two units. It We can give it in clock cycles also, and we can give it in seconds also. If we give it in clock cycles, then this is the formula which I have shown to you. This is the formula for clock cycles. And if we want to give it in seconds, okay, we don't want to calculate it TB clock, we don't want to go for the TB clock and all these things, then you just put TBPRD value in seconds, 1 by FPWM for up or down counter, and for up and down counter, TBPRD value 1 by 2 into FPWM. Okay, so here you see here we have 10 kilohertz, 10 kilohertz PWM pulse. So for 10 kilohertz, how can we find? So go to the formula 10 kilohertz. So we have TB clock of 100 megahertz and FPWM is 10 kilohertz. So when we find it comes 10,000 and 10,000 minus 1 is 4 times 9. So I have given the TBPRD value as a 4 times 9. Okay, see this one. I have given the TBPRD value 4 times 9 for 10 kilohertz pulse. Okay. Similarly, the compare value I have given. I have told you, I will tell you how it will be calculated. Similarly, if we go for the time TBPRD value in seconds, then see I have given only 1 by FPW. We Here we are generating 20 kilohertz pulse. So I have given 1 by FPWM, 1 by 20 kilohertz only. We don't go for calculation of TBPRD value. We can directly give 1 by FPWM value to generate the TBPRD value in seconds. So this is more simpler and okay. Now we go for the compare event waveforms. Okay, how the accent qualifier will set up and clear. So this is the TBPRD value which I have told you for the maximum peak is the TBPRD value. Now the accent qualifier, when we go for the up counter, when the up counter is equal to 0, this is the 0 time which is starting. This is the compare B position, this is the compare A position, and this is the period position. So in case of up counter, when the zero is happened, it will go to set mode. Okay, it will go to the set mode when and EPWM for APWMA we focus on only compare A value. Okay, so when the compare A comes, it will go to clear. So when again you see the zero and zero will come, and this is also the position of period also. So if we are focusing on zero, so we don't have to focus on period. Okay, so throughout the time we have to disable the period, means we have to do nothing for the period. So again will zero come, then as previously I have said that I have uh, I have set for the zero. So again here when zero come, it is set. Then again compare a clear, then again set for the zero. Similarly for compare EPWMB, for zero it is set. Then again compare B comes, it will clear. Then again zero will come, it will set. That's how we uh, that's how we define the action qualifier for the up mode. Similarly for the down mode, we can define the action qualifier, and this is the action qualifier for the up and down mode. Here you can see for EPWMA pulse, when it is zero, then we have to do nothing. When it is compare A, then we have to go for set. Then then we have for the compare B, do nothing. Then with compare A while down, then we have to clear. Again, when compare A comes for the up, it will go up and down like that. Similarly for EPWMB, moving to the next slide. This is the compare value calculation. Uh, for up and down cycle, how we calculate the compare value. Okay, for up or down counter in clock cycles. In clock cycles, if you want to calculate the compare value, so suppose if you want to generate the 30% duty cycle or 50% duty cycle. Okay, so D value means in fraction it will 30%. If we go for the 30%, it will the D value is 0.3. Okay, and if we go for the TBPRD value, which is like 10 kilohertz, so I have told you that TBPRD value is 4 times 9 for 10 kilohertz. So zero point 0.3 into 4 times 9 plus 1 minus 1. So from this way we can find the duty compare value for generating the 30% duty cycle. Similarly, if you want to calculate the compare value for 60% duty cycle, then you have to put zero point 0.6, then TBPRD value 14 kilohertz 4 times 9 plus 1 minus. From this way, you can find the up or down on compare value in clock cycle. And if we want to calculate in percentage, means up and down value, we don't go for the TBPRD, up or down value in percentage. So we have to only multiply D with 100. Similarly, for up and down counter, we have to put compare value formula 1 minus D into TBPRD. So if we want to create 30% duty cycle, so I have to put 1 minus 0.3, means 0.7 into TBPRD, 0.7 into TBPRD. And here TBPRD value you should take for the formula of up and down counter by which we can calculate the TBPRD. Okay. Similarly for up and down counter, if you want to go for the percentage, then compare value is 1 minus D into 100. I can see this. In this one, I have given the TBPRD value in terms of clock cycle. So for 10 kilohertz, 4 nines, compare value, I have given in clock cycles. You can also choose the compare value in terms of clock cycles. Here you can see compare A units, clock cycle and percentage. So if you select the clock cycle, then and I have selected the input port, means you can give the compare value through the input port. So the input port is coming. See this the input port the compare. This is the input port for compare B. So to compare B, and I have to generate 30. I have to generate 30% duty cycle. So for 30% duty cycle, I have told you 0.3 into 10,000 minus 1. So this is the value. Similarly for compare B, zero point 0.6 into 10,000 minus 1. So this one comes. Okay. And similarly, when we go for the percentage value, then you just percentage value you see. If we go for the percentage value, then you have to just put the in percentage, in terms of percentage, means duty cycle into 100. If you want to create 30% duty cycle, 0.3 into 100. 0.6 into 100 for 60% duty cycle for up count mode. Similarly, for up and down count mode, I can show you. See this for up and down count. Okay. For up and down count mode, similarly, we have selected TBPRD value in terms of clock cycles. Okay. Here it is 20 kilohertz pulse. Okay. So I have told you the formula. Through formula, when we find about the TBPRD value in clock cycle, then it will come 25. Similarly, for if we go for the compare value in terms of clock cycles, then I have told you that the formula is 1 minus d into TBPRD. Okay, so 1 minus d, if we want to create for 30%, so 1 minus d, 1 minus 0.3 is 0.7, then we have to multiply with the TBPRD value, then we can fed to the compare value to the A and compare value to the B, EPWM works. Okay, similarly, in case of Similarly, if we want to go for the percentage and seconds, so in case of TBPRD value, I have told you if we want to generate the pulses of a particular frequency in terms of, and we want to give the TBPRD value in terms of seconds, so only we have to do is 1 by 2 into F. So I am generating 20 kilohertz pulse, so I am giving the value TBPRD 1 by 2 into F, 1 by 2 into 20,000. Okay. And similarly, if we want to give the compare value, then I have told you that 30%, I have to give it 1 minus d into 100. So 1.3 into 70. And for 60%, 1 minus 0.4 into 100. So 0.6 into 100. So 40 is. So this is for the so now in this slide, I have generated the PWM pulses in up or down counter mode. This is the up mode in which 10 kilohertz PWM cycle, 10 kilohertz frequency is given, and the duty cycle is 30% and 60%. So this is the way you can see this one. And again, we go for the PWM block settings. I will tell you how to set it. Okay. So for TBPRD value, you have to give it through the input port, and you have to select it clock cycle. Okay, clock cycle you have to select. You can select also in second. Then you go for the counting mode, which is up. Okay, synchronization accent you have to disable it. Here we can see the time-based clock and high-speed clock. T-scalar divider is 1. Then we go for the EPWMA. EPWMA, I have told you how to set it. Give this slide. EPWMA, how to slide 0, set, and period do compare, we do compare to clear. So again, according to that, I have selected for the EPWMA. Only for the EPWMB, I have selected. Okay. Compare is I have selected in the clock cycle. You can also select in percentage, and I have to select via the input port. So I have given the input port here. Input port deadband. I am not giving some deadband also, so not doing anything to it. To apply and okay. Then we have see so here you can see this is cycle. This is the 60%. See 6% duty cycle. First one is 30 cycle of 10 kilowatts frequency, and the second one is of 6% duty cycle with 10 kilowatts frequency. Okay. Coming to the next slide. Why deadband is necessary? Okay, when we have a particular when we are going to run some converter or inverter, rectifier, whatever a particular like in which two switches are there. Okay, so at a time, if both switches are on, then it will get short circuited. Okay, so actually we have to operate this particular leg with the help of complementary PWM signal. These PWM complementary signal have some switching so that the both switches will not at the same time. If both switches will be on at the same time, it's short circuit. We have to keep some in the complementary pulse of the PWM pulses. We have so if we generating from each one channel, one A and there, we have to make complement with the help. We have to make it complement, and we also want have to give the deadband also. Okay, some deadband, some 3 microsecond or 5 microsecond deadband should be there. So here we can see this is the original wave, original PPD. Okay, so when we give the delay in the rising edge, okay, so it will become like when we give the delay in the falling edge, then we can see the rising gauge is same as it is, and the falling gauge is delayed version, so somewhat delayed. Similarly, here we can see the active high complementary mode. This is the complementary pulse generated, and this is in the active high complementary mode. Means see, this is the original pulse. The first one is original pulse. Active high complementary I have switched and I have given, and the delay in the rising edge also and the falling edge also. So we can see the active high complementary pulse is something, the width is reduces. Then the upper switch pulse width is reduces. Similarly, if we go for the complementary pulse, then it pulse width increases. Okay. Similarly, when we go for the active low complementary, then this become the original pulse is this, then the higher pulse is like this, and the lower pulse is like this. Okay. When we go for the active high, then the both pulses would be like this. When we go for the active low, the both pulses will be like this. Right? So among these, we can use any modes: active high complementary, active low complementary, active high, and active low. All different complementary modes we can use. We have to use according to your application, according to our application. In our applications, we want the switches not to turn on at the same time. Okay, so we go for the active high complementary. In active high complementary, you can see when the first one is 0, then the other is 1. No duration you can see when the 0 and both are 1. Okay, since both are 0 can happen, both 1 should not happen. So here 0 1, here 1 0, also 0 0 0. Okay, so here we can go for the active high complementary, but in most cases the this one active are 1. Here also both are 0. Here in also active low complementary, you can see here both are 1. So we can't use active low complementary. The dead band is given. You see just this is the dead, how we keep the dead, how we generate dead complementary with the dead. Okay, so this is the AWM module I have taken. Okay, so this is the 10 kilohertz PWM process first we generate. So for 10 kilohertz, this is the up mode. So in up mode, we have to give 2999. You can find 1000 kilohertz by 10 kilohertz. This is the compare value. VPRD you can see for 10 kilohertz, it is 4 times. Actually, in this I have given inside specified by I have given in, but you can take also from output port, input this input you can download also. As a compare value, I have told you how to calculate it for formula, which is plus one gain value which is 4 times 9. Okay, this come. Here you can see if we want to generate the deadband, we go for the EPWM 1A. We set according to action qualifier, which I have told you in the up counter. We don't have to enable the EPWM boundary. Okay, we don't have to enable it. We don't have to invert it. We don't have to do it anything in this one. And just go for the deadband unit and just click on these EPWM1, EPWM1B. Both you have to uh, turn it on so that we can see the deadband. Here you can see the deadband polarity is there. Okay, deadband polarities. I have told you 4 types of deadband polarities there: active, high, complementary, low, complementary, active, high, and active low. I have selected active, high, complementary. Okay, then rising age delay you have to select PWM, falling age delay. Okay, now to select the value. Okay, so see this slide. How to select the value? If if we have the TB clock, which is system clock out by 1, means if the TB clock is equal to system clock, okay, then this is the delay we can produce, and this value then this can produce. This one we have to select the deadband value dbFET. Deadband falling is delay, deadband rising delay. You have to select this one. I have selected 500. 500 stands for 5. Okay, so uh, delay is 5, including the rise delay and including its delay. By both, if they select the DB, FED, DBI, ID both 500, then it will create some 5 microsecond delay. It will create some 5 microsecond delay. So this one, you can see deadband RED and FED is given 500 and 500. Here I have not enabled the half cycle blocking. Okay, if I will enable the half cycle blocking now, then it will be clock is equal to system clock out by 2. Then it will generate for 510 microseconds. Okay, if enable the half cycle. If it don't enable the half cycle clocking, then it will generate the 5 microseconds. According to TB clock is equal to system clock. We have not enabled the half cycle clocking. So for 500, 5 microsecond delay you can see. So here I have taken some also. You can see you can see you can see this is the active high complementary pulses and this is the lowest pulses. Previously it is 30% of duty cycles. So you can see it is 5% duty. You see 25% duty cycle. Means previously we have the 30 microseconds, but right now I have given the 5 microsecond delay, so the width is reduced to 25 microseconds. You can see the 25 microsecond width is there, and the duty cycle changes to 25%. Similarly, for the second one, I have told you it will increase the delay, so 5 microsecond it will the delay is added. So previously the width is some 60%. 60% duty cycle is there. The lowest means complementary. If you see 70% duty cycle is there. 30 and 70. Yeah, 30 and 70 are there. Cycle is become can see it is the duty cycle is 65 minutes. Now we give next slide PWM entry. We want to generate the PWM entry for, and you don't have to do is in case first, you just have to same thing here. Set according to the action point 5 EPWMB. You have to turn it on now for the complementary process. Enable EPWM, and you just have to select the inverted. Then you can get the inverted pulse. Okay. So this is the inverted pulse you can see on the output. This is the 30% duty cycle, the first one, and the second one is of 70%. Now this is the slide in which I have told you that how to generate the PWM pulses up and down, up and down. But I have told you how to give the TPPRD value, how to keep the compare value, compare B value. So according to that, I have given that values and have generated two pulses, which is of 30% and 60%, 30% 60% duty ratio. You can see the first 30 duty cycle, the second one is of 60% duty cycle. Moving to the next slide. This is the up and down counter mode. Previously, I have taken all the clocks, the TPRD value in clock cycle, compare both in clock cycles. Okay, so in clock cycles, we have to go through some calculations. We have to, but if we go for the seconds and percentages, then you don't go through the formula. If we want to generate 20 kilohertz pulse, then you give 1 by 2. If you want to give 30% duty cycle, you give 1 minus day 20 and 6%. To give 140. If the output 40% duty cycle, 6%. Okay, moving to the now we page out page shifted PWM pulse. We get the PWM phase shift. Okay. So formula will go for down, and this is the up and down. These in clock cycle. How we see the value in PWM block, you can't in seconds. It is in clock cycle. So you have to give it in clock cycle. This is the formula vary clock is equal to PWM block. In our PWM clock by 2 megahertz, and TB clock is megahertz. In our case, TB PWM clock. So we this form, which is equal to plus 1 into phase 360 plus. Okay, phase you want like you want 30 degree, 30 degree according to requirement. When TB clock and EPWM go for this form. For up and down form also, this clock and EPWM equal PHS value 2 into page 60 plus 2. When this TB clock is late, clock will go to the TB equal to TB clock into 360 plus. And this is set according to can recognize your sequence. This this for recognizing two phase shifted. Okay, two signal synchronize this diagram and three signal you this side. You can see the EWM, and there is sync in and sync channels are there. Here you can see sync in is channel, sync is not connected. It is can be disabled. Okay, but sync out you can see it is connected to counter equal to 0. So when we set the EPWM block when we configure the EPWM block, then sync out you have to set for counter equal to 0. And when we go for the EPWM2 block, then in case of sync in should be connected to the phase. Okay, phase. If I will show you. And this no sync in is connected to the sync out of the first. See this one. Sync in is connected to the sync out of first, and it is also connected to the phase shift value also. So sync in connected to the phase shift and phase shift value also, and sync sync out is connected to the phase shift value and sync in is connected to the sync out value. Okay? Similarly, when we go phase shifted process, you see the sync out is connected to the counter equal to 0, first one. The other one, sync out, is connected to the sync in value of the first, and again the phase shift. Similarly, when we go for the third, sync out is connected to the sync in and also for the phase shift value. Okay, now I will show you how. This is for up counter mode, 20 kilohertz pulse generation with 30-degree phase shift. CEPW. Sync in and sync out. Sync is disabled. Sync out is connected to counter equal to 0. Okay. Then we go for the X. Sync in sync is connected to the phase shift value. I have told you sync in is connected to the phase shift value and sync out is connected to the sync in. Okay. You can see in the slide, sync out is connected to the sync in and phase shift value, and sync in is connected to the sync out. Similarly, for the third, three phase shifted pulse. This will now three phase shifted pulse settings. Okay, first setting you can go. The first setting is see this one, the synchronization disabled, sync output is control equal to 0. The second one you see, synchronization action is connected to some phase shift value, and the sync output is connected to the previous EPWM1. Okay, actually this is the process of linking of all the three EPWM modules. This process is called as master slave modules. Okay, here the first one is actually a master. Actually, one EPWM module is a master and the other two are slave. So we have to link the slave modules with the EPWM previous module. Okay. So see, I have linked the second EPWM module, EPWM link TBPRD. I have linked with EPWM and I have selected these settings according to I have told you. Similarly for EPWM2, for EPWM2, if you see, I have linked the EPWM link with EPWM1. Okay, so when we go for the slave module, we have to link it with the previous. We have to link it master module. Okay, when we go for the one-time phase shift, when we go for the two-time phase shift, when you want to create the 3 or 4 phase shifted signal, you have to link with the master unit. Okay, EPWM1, and you have to select the synchronization in and synchronization out according to the diagram which I have shown to you. In synchronization action, you have to keep the value of phase shift.
And this is the synchronization output you have to link with the synchronization in the previous. And you know how to give the TPPRD value, how to give the compare value. These are in the clock cycle. This one is in the percentage, so I'm giving the percentage. Now, how to calculate the phase shift value? I have told you the formulas for a counter, how to calculate the phase shift value, and this is for the 30-degree phase shift, and we want the next pulse would be 60-degree phase shifted from the first pulse. So this is the point. So okay, this is for the up counter. Okay. Now, when we go for the up and down counter mode, then the same thing is happening. You have to go for the same settings, but you only have to change the phase shift value and you have to change the TPPRD and compare value according to you. Similarly, for three-phase shifted signal, if you see, similarly, if you see the three-phase shifted signal, then you only have to change the phase shifted value. Now we go for the next slide. So this one, you can see 20 kilohertz pulses with 50% duty cycle, and these are the phase shifted by 30 degree. You can see the result. See this one, the first one is 20 kilohertz, the second one is also 20 kilohertz, and the both should be shifted by 30 degree. So you can see here, both should be shifted by 30 degree. This is the 30 degree phase shift. Here you can see each block is of 10 microseconds. Here you can see. If you find the 30-degree phase shift, how much the time is of 30-degree phase shift, then it will come around 4.1 microsecond. So you can see here the each block is of 2 microseconds. So 2 plus 2, 4 microsecond delay is there. So it means 30-degree phase shift. Now we go for the next. Phase shifted. Here we have created three phase shifted pulse. I have told you three phase shifted. The first one is the reference. The second one is 30-degree phase, and the last one is 60-degree phase. You can see 30-degree phase shift, and all the phases are same. The first one is also 20 kilohertz. The second one is 20 kilohertz. The third one is 20 kilohertz, and all the duty cycles are also same, but they are phase shifted. Okay, you can see the phase shift. I have told you that each block is of 2 microseconds. So this is the reference, and the second one actually stay before the 4 microsecond, after 4 microseconds. So there is 30-degree phase shift, and the last one is staying in 2 to 4, 6, 8, 8 microseconds. So it is 60-degree phase shift. Okay. Similarly, for the up and down counter mode, we have created the pulse width. You can see also the same phase shifting is coming. Same phase shifting is coming. I have kept the same frequency and same phase shift, so the same result is coming. For the signal, same result is coming. With the next slide, new conditions for when we is 320 f to 20 micro each ADC pin is actually only the unipolar voltages. Okay, if you sense the current sensor output, if you sensing the voltage, if you sensing the pressure and or anything, actually it will generate the corresponding voltage, and the corresponding voltage limit which which we can give to the C2000 microcontroller as an ADC input, it is only 3.3. For safe purpose, you can only give volt to the microcontroller ADC. Okay, so whatever the whatever the sensor, current sensor or voltage sensor you are designing, okay, its output is voltage. Current sensor output is also voltage. Voltage sensor output is also voltage. But you have to step it down on below 3 so that you can it to the ADC input of the microphone. Okay. But when we sense the data which is bipolar in nature, like if we consider the inductor current, some sinusoidal pulse, which have positive and negative also, and in T2000 can sense positive voltage, which is below the 3 volt. So how we can sense that data which is pulsating in nature, which has the positive peak also and the negative peak also, how we will sense it. So so before giving with suppose our sensor is sensing some voltages which is pulsating in it. Okay, so we have to give it to the C2000 microcontroller. How will I will do? So firstly you have to make it positive and below 3 volt. So at that time you need the signal conditions. The signal conditions of we have to for instance according to is 1 point. Okay, whatever the voltage we are sensing, you just have to design your sensor so that the voltage will automatically reduce to plus minus 1.5. Okay, then you have to use this op-amp setup. The first one actually what it does is it subtract 1.45 volt from the let's suppose we have sinusoidal signal of 1.5 volt plus and minus peak. Okay, plus 1.5 volt and minus 1.5 volt. We subtract 1.5 volt offset, then the whole signal will come down. Okay.
Gaurav,
Yes, sir.
your voice is not breaking, so maybe some louder if possible.
Okay, okay. When we signal conditioning circuit, the first which is through the op-amp, it will it will it will it will the sinusoidal which is nature with the upper line. So see it is minus volt, and this setup, this op-amp setup, it invert the overall pulse. It invert the overall pulse, so we can get the output voltage which is 3 volt pulsating. Okay, now we can give it to the ADC input of the C2000 microcontroller. So we have some ADC and DAC modules in C2000 microcontroller. We can see some we have in F2837090 we have three ADC modules. Basically, F287XD series has four ADC modules, but in F28790 we have three modules A, B, C, and each modules have 16 channels. You can see from 0 to 15 we have 16 channels. Okay, single-ended which is of 12 bit means if this pins if this pins sends the data, then it will convert to the corresponding 12-bit digital value. Okay, when we go for the differential input pins, then we have to input with two pins. Suppose we want to give the differential input we want to sense with the help of ADC block, then we have to give positive input ADC in G and the negative input to ADC input 1. From that way we can sense the differential input. Okay, similarly for the 2 or 3, if we want to sense from the 2 or 3 terminal, then ADC input 2 we have to give the positive input, and for ADC input we have to give the negative input. So if ADC block is sensing the differential input, then actually it will convert the 16-bit digital data. Okay, and it is sensing the single-ended input, then it is converting into the 12-bit data. When it is sensing the differential input, then it is converting it into the 16-bit data. Okay. Now we have some ADC and DAC module. Let's suppose DAC channel we can here in this we can we want to see analog value which we are giving actually which we are giving actually we can sense it through the DAC channel. Okay, so how will we send it? Firstly, we have to create some analog value. How will we create the analog value? Some sinusoidal signal. This is the sinusoidal signal. Okay, and you know the sinusoidal signal have plus minus plus 1 volt peak in the positive direction, minus 1 volt peak in the negative direction. So we know that the signal microcontroller ADC or DAC pin can take only 3 volts or below 3 volts. So we have to shift it. We have to make it positive. So I am adding 1. Okay. So here we can get the sinusoidal pulse, which is of 2 volt peak. Okay, which is of 2 volt peak because I have added 1. Then now we want to convert it into analog value, digital value, because I am using the DAC channel. I want to see the output with the help of DAC channel. So we have to convert it into digital value. So how will I convert it into digital value? So we know 3 volt is corresponding to 3 volt corresponding to 4095 in digital data. Okay, so if we want to convert that analog value into digital value, then we have to multiply it with 4095 by 3. Okay, so the digital value come which is below the 4095. Then this digital value sends with the help of this DAC block, and we can see the DAC output with the help of some DAC output A pin. DAC output A pin is some 30 number pin. So you see the output 30 number pin. Okay. Here the same data which we are sensing through the 30 number pin of DAC output. The same data we can fed it to the ADC input also. Okay. So in this slide, I am generating a particular sinusoidal pulse. I am sensing that sinusoidal pulse with the help of DAC module. Then that sinusoidal pulse is given to the ADC module. Okay, hence I have given this DAC output to the ADC input. So I have taken output from the 30 number pin. If you suppose from 30 number pin, which is DAC A output, so it will be given to the ADC channel of 29 number pins. ADC, I have selected ADC into, so it is 29 number pin I have selected, so I have given to it, and again it will convert the analog value into digital value, and then this digital value is fed to the DAC channel, and we can sense the DAC output from the P output channel. Going to the next slide. This is the MPPT closed. If you want to drive your switches, suppose if you driving the switch of boost converter which is working in MPPT mode, and if you want to run it in closed loop, then how will you do it? Okay, so firstly you have to sense the voltage, you have to sense the current, the voltage sensor you have to make the current sensor, the voltage sensor and current sensor. First you have to check the voltage sensor and current sensor, both outputs should be below 3 volt. Then after you use the ADC block, you give input to the ADC block with the help of 29 pin and 26 number pin for this current sensor. Then you have to convert it. It is sensed, then it will convert it to some digital value. Okay, analog to digital converter. It is sensing analog value and it will convert into digital value. Okay, so digital value is converting. Now we have to multiply it with some gains so that it will convert into analog value. Okay, so it will convert the analog value. Double data conversion block is taken so that we can consider the point value also. We can consider the point also. Here we have considered the in 16. Here it can take the positive and negative value also. Here some rate transition block is used. Whenever some data transfer is happening now, you have to use some rate transition block because some data transfer rates mismatches. Okay, means suppose you are getting VPB and IPB both in some different time interval. So rate transition block, what it does is is it make the data transfer simultaneously. Okay, means at the same time you can get the PPV and IPP. So if there is some delay in current sensor also, you can get at the same time. Okay. So here some PSO block I have used in which coding is there, and VPV IPV it is sensing through the ADC block. Then it will create some duty cycle, and according to that it will double is used to convert it into point and decimal values also taking some rate transition block is also used. Then it will convert into percentage value. Then it will be converted into percentage value. Then we give this value to the compare block of the EPW impulse, and compare block EPW impulses. We have told you that how to give the time period. The time period is given in TPPRD clock cycle value. So I have taken 1999. Okay. And the compare value is generated from this, and from this way you can take the output from the 40 number pins or whatever the pins you have selected in the EPWM block, and you can drive the boost converter switch, and you can get the desired output of MPPT. Okay, so that's all of my presentation. If anyone else have some queries, then they can reach. Am I audible to everyone?
This Gaurav, this PSO block is this PSO block actually it was created or it's already available in the MATLAB.
No. You have to write the code. See this one. I will show you. This one. Okay. You have to sense the ADC input voltage and current. You have to use PSO block in which coding is written. Okay. If you go for some other algorithm like P&O, incremental conductance, or some AI and fuzzy logic, some AI and ML method, then you just have to put the coding of it. Okay. And then you have to generate the corresponding duty cycle by sensing the data, and you just give it to the EPWM block, and you can generate the duty cycle EPWM process, and according to that you can control your switch.
Any more queries?
Hello, sir. Good morning, sir.
Yes.
Sir, I am new to this one digital controlling part, sir. So let me know
Okay.
if at the end of this workshop, this all example files are shared on the group or not, sir?
If you want,
When you
I
explain
can
this
give you.
code, sir.
I'm
For
not
the
getting
basic
PSO code.
understanding purpose, this GPIO pins and this one EPW blocks, I think how to connect. You connect a simple circuits. Shall we this one?
Oh, you want the simulation?
Yes, sir. Yes, sir. For our understanding,
Okay. I can.
why, because I'm new to this one digital part.
Okay. I will share you in the group.
Actually,
Okay,
the
sir,
recorded
not,
session, just listening. Actually, the recorded session we are going to circulate. Now, from there we'll get that one, so you can easily replicate. After that,
okay,
if
sir.
you face
Okay.
any difficulties, so you can. I will share his number definitely. My mail ID. So
Okay,
you
sir.
can.
Okay. That's
So
good, sir.
that is
That's
great.
good, sir.
Yes, yes.
Okay, sir. Thank you so much.
Thank you. Is there any other queries? Otherwise, we'll declare for the launch. Okay, I hope there is no queries. So thank you, Gaurav, for your valuable time and your in very good presentation, because elaborately you have discussed a lot of things. Okay, so thank you all of you. Again, we will meet on next slot approximately 3 p.m. So I'm requesting all of you please be online. Okay, that time. So on now we will take that section. Okay, thank you all of you. So we can go for lunch.
Thank you.
Bye.